We have an interesting curve here, y equals sine of cos x. And we've got a sketch of it. We're told, and we're asked to find a, c, and b. So let me deal with b to start with. That is going to be when x is 0. So y will equal sine cos of 0. Cos of 0 is just 1, so it's sine 1. So b will be 0 sine 1. Okay, next a and c. That will be when y is equal to 0. So we're going to get sine of cos x equal to 0, which means cos x would have to equal 0, or it could equal any multiple of pi, like pi minus pi. But actually, we know that cos x is always less than 1, so I can reject those and just look at cos x equals 0. And that's going to give me x is pi over 2. And I see I've got a negative 1 as well. The first negative 1 is going to be minus pi over 2. So therefore a is going to be minus pi over 2, 0. And c is going to be pi over 2, 0. We have it. Next up, we're asked to prove that b is a stationary point. So we need to find dy by dx here. And that means differentiating sine of cos x. Now we can just use the chain rule by looking at it. So essentially we differentiate what's inside, and that's going to be minus sine x. And we times by what we get if we differentiate sine x with respect to cos x. And that's going to be cos of cos x. Of course, you can write it more formally if you prefer. So when x equals 0, dy by dx, I should probably say at b, when x equals 0, dy by dx is therefore equal to 0 because it's minus sine 0. You could argue that because it's a proof question, I should probably show a bit more working actually, so let's go for that. It's going to be minus sine 0 times cos. Cos of 0 is just 1, but this is going to be 0. And therefore, I think that's enough. Therefore, b is a stationary point. We're then asked to show on the interval 0 to pi over 2 two inequalities. And the first one, well, if you sort of forget the cos x for a second, we're looking at the fact that sine x is less than or equal to x. And that is something that actually comes out of this, related to the small approximation for sine. So in fact, sine x equals x minus, this is a Maclaurin expansion. In A level, you tend to be given that for small angles, this is approximately equal just to x. In fact, you get that. But the key thing is that sine x is always less than or equal to x. And they're equal when this x is equal to 0. So this is true. This is going to be got that cos x is greater or equal to 0 for x greater or equal to 0, which is one of the conditions, and therefore sine of cos x is less than or equal to cos x for 0 to pi over 2. And when is it equal? Well, like I said, it was equal when this x bit is equal to 0, so it's equal when cos x is equal to 0. So equal when x is equal to pi over 2. For the second inequality, we need to look at this bit here, the fact that region OCB is convex. And what this is kind of telling us really is that this never sort of goes back up. The gradient is actually decreasing. The second derivative is negative. And what it means is if we were to draw a line from B to C, then this equation of this line, or the value of the function y is always going to be less than this bit here. You can kind of see where, if you didn't spot that straight away, well, we know we've got sine 1 in our answer, so it's got to have something to do with this. So basically, we want to find the equation of BC. And for this, the gradient is going to be the change in y over the change in x, or y2 minus y1 over x2 minus x1. So if we pick that furthest bottom right coordinates, then the x coordinate or the y coordinate of that was 0, and the x coordinate was pi over 2. And if we pick B, which was at the top of the peak, the x coordinate was 0, and the y coordinate was sine 1. So we're going to get, and then if I divide by pi over 2, it's the same as timesing by 2 over pi, so I'm going to get minus 2 sine 1 over pi. Okay, this is the equation of the line. And which coordinate do we substitute in? Well, in the final answer, we've got sine 1 in 2 terms. So I'm going to go with that. It shouldn't matter. We should be able to. It should be fine either way, actually. But if I use that that b value, then I'm going to get y minus sine 1 equals minus 2 sine 1 over pi times x minus 0. So it's just x. And y is going to be sine 1 minus this. I can factorize out the sine 1, so it's going to be 1 minus 2 over pi x. That's not quite like in the normal equation form, but it is actually now ready for this. So I know that this here is less than or equal to sine cos x. Since BC never goes above the curve. And again, we're asked when they're equal. And it's going to be at B when x is equal to 0, and at C when x is equal to pi over 2. Finally, we're asked to show this relationship here, not to find the integral of this, thankfully, but to show that it lies between these two values, and it's going to be using the two results that we just obtained. Now let's deal with the slightly simpler one to start with. We have from before, so this is part D. From above, sine cos x is less than or equal to cos x. And therefore, the integral is going to be less than the integral of cos x. And we can change this to a less than sign. So not equal since sine cos x only equals, like if they were equal everywhere, then yes, this would be, the inequalities would be equal. But we can say, we can be sure that this is going to be less than, not equal since sine only equal to cos x in one place. And this here, I'm going to jump straight to it. It's going to be, if we evaluate it, it's going to be sine x when we integrate cos x, evaluated between 0 and pi over 2, which is 1. And so we've got the first bit essentially. We've just worked out this bit here. Just write that down. Now we have this slightly more awkward bit to look at. But remember from above, we've got this other inequality that this is always less than or equal to sine of cos x. Now remember, this was the equation of BC. And actually, sorry, it's again a less than sign. I don't think I even need to justify it. I've justified it above. This thing, I can actually, this is just a constant, so I can take it outside the integral. And I get to integrate, so I get x minus 2 over pi times a half x squared, so it's just going to become 1 over pi x squared. And when I square pi over 2, I'm going to get pi squared over 4. They're going to cancel. So I'm left with pi over 4, because pi over 2 minus pi over 4 is just pi over 4. A half minus a quarter is a quarter. And that's all we needed. Okay, that's a pretty neat result. It's an interesting sort of doing integrals and not actually finding the value, but finding the bounds of them using, using different ideas. And I'm not going to write the final thing down. I'm just going to write that the result follows. Right, I hope that all makes sense. Well done. Keep going.